Welcome. This is going to be the start of our chapter 7, which is about exponential and logarithmic functions. So the first half of this chapter, we're going to talk about exponential functions. So an exponential function is something of the form y equals a times b to the x, where a is non-zero and b is greater than 0 and also not equal to 1. Now, a needs to be non-zero because if a is 0, then this 0 times anything is 0, and you just have a constant function. We don't want to call constant functions exponential functions. If b equals 1, 1 to any power is just 1, so this just simplifies down to a. So that's a constant function also, and we don't want to include that. And if b was negative, if I had 1/2 as my exponent of x, we know that 1/2 is the same thing as a square root. So the square root of this negative b would be undefined, and that would happen periodically every time we got an exponent whose denominator was an even number. You'd have undefined things over and over all over the place, and you'd really have something that was discontinuous and not very well behaved. So we don't want to include those either as exponential functions. So the value for our base, this number is called the base. This is like our exponent. This is a coefficient. But the value for our base has to be a non-negative number that is at least 1. So what we'll talk about here in this first section, we're going to talk about graphing exponential functions. And the general form for our exponential functions that we'll be graphing are of this form. So y equals b to the x minus h plus k. One thing that we have to be careful about when graphing exponential functions is that they can get, the y-coordinate can get very big or very small very quickly. So one of the hallmarks of an exponential function is that they grow or decay rapidly. So we have to be a little bit careful when we're choosing our x values for our function. So usually the way that I choose my x values is I'm going to do h minus 2, h minus 1, h minus 0, h plus 1, and h plus 2 is how I would choose my x values. And then to find the y values, I can just plug that in. What it'll simplify down to, though, if we look at this closely, if I plug in like h minus 2 for x, the positive h and the negative h will cancel. So really I'm going to have a times b to the negative 2 plus k. And then similarly, I didn't include the b here because you have b to the 0, which is just 1. We know that from last section. So you could do that too. You could plug in the x values, or you could use to find the y's, or you could use that little formula to calculate them. It doesn't really matter. So that's going to be how we're going to find our exponential functions. The domain for exponential functions is always all real numbers. And the range is one of two situations. So if the a value is positive, it's going to be k to positive infinity. Note that that's a parenthesis on both ends. And if the a is negative, it's going to be negative infinity to k. Again, note that there's a parenthesis on both ends of that interval. Exponential functions do have one key feature, which is a horizontal asymptote. And it's easy to find because it's always at y equals k. So all exponential functions have a horizontal asymptote, and it's always at y equals k. There are two types of exponential functions. So there's exponential growth. That's where we have a b value greater than 1. So our graph is increasing as it moves from left to right. And then we have decay. That's when our b value is between 0 and 1. Remember, the b is always non-negative, and it's not equal to 1. So decays are between 0 and 1. And this is assuming that a is positive as well. We should say and. It would be the reverse if a was negative. So by that I mean that the a being negative is going to turn what would normally be a decay graph into a growth graph, and what would normally be a growth into a decay. So let's go ahead and draw some graphs here and do some examples of graphing some things. Okay. So let's just do a couple of examples. So right away, I would identify my values for a, b, h, and k. I'm going to look at my value for a and b. I notice that a is negative and b is positive. This is a decay situation, so my graph should be decreasing as I move from left to right. I can then generate my xy points to make my graph. So again, I'm going to do -2 plus h for my x's, -1 plus h, 0 plus h, 1 plus h, and 2 plus h. So when I plug those in, I'm going to have -3 times 2 to the -2 minus 4, and then -3 times 2 to the -1 minus 4, -3 times, well, really just -3 minus 4, I think is the way I wrote that shortcut. -3 times 2 to the first minus 4, and -3 times 2 squared minus 4. You could also have written like -3 times 2 to the 0 there if you wanted to. It's the same thing as 1 though, right? So if I simplify this, this is -3, -2, -1, 0, and 1. 2 to the -2 is 1 over 2 squared, or 1/4. 1/4 times -3 is -3/4. And then minus 4 is -4.75. 2 to the negative 1 is 1 over 2, times 3 is negative 1.5, minus 4 is negative 5.5. Negative 3 times 1 is negative 3, minus 4 is negative 7. Negative 3 times 2 is negative 6, minus 4 is negative 10. And negative 3 times 2 squared is negative 3 times 4, which is 12, minus 4 is 16. So I'm going to go ahead and draw my graph then. So 1, 2, 3, and 1. And I have to go down to 16. So I'll probably go by 2's. 2, 4, 6, 8, 10, 12, 14, 16. I'll draw in my asymptote here. So my horizontal asymptote is at y equals k. So in this case, that's negative 4. So again, remember my tick marks are going by 2. So that's y equals negative 4. And now I'll plot my points. So I have negative 3 and negative 4.75, negative 2 and negative 5.5, negative 1 and negative 7, 0 and negative 10, and 1 and negative 16. So I'll follow my asymptote, go through my points, put an arrow at both ends. And you see that as we're moving from left to right, the graph is decreasing quite rapidly too, right? You see that the hallmark of an exponential function is that its slope is increasing, or increasing rapidly, or decreasing rapidly, depending on whether it's growth or decay. So again, the domain for something like this will always be all real numbers, so negative infinity to positive infinity. And since the a is negative, our range is going to go from negative infinity to k. And that's it. Let's do another, and then we'll move on to something else. Okay. So another example, again, I'm going to start by listing my values for A, for B, for H, and for K. So these two together tell me that this is also decay. Again, the A is positive, and the B is between 0 and 1. So we'll make our XY table. I'm going to pick my points as negative 2 plus h, negative 1 plus h, 0 plus h, 1 plus h, and then 2 plus h. And then my y coordinates are going to be a times b to the negative 2 plus k, a times b to the negative 1 plus k. Oh my goodness, my a is 3. My apologies. A times b to the 0 plus k, or you could just leave the b to the 0 off. That's fine also. Same thing. 3, or a times b to the 1/2 plus k, and then a times b to the 1/2 squared, or a times b squared to the minus k. And if we simplify, negative 2 minus 2 is negative 4, and then with negative 3, negative 2, negative 1, 0. 1/2 to the negative 2 is 2 squared. 3 times 2 squared is 12. 12 minus 1 is 11. Again, you could do this in your calculator if you wanted to, that's fine, but I'm going to just do it in my head. 1/2 to the -1 is 2. 3 times 2 is 6, and then -1 is 5. Anything to the 0 is 0, or is 1, so 3 times 1 is 1, -1 is 2. 3 times 1/2 is 1.5, -1 is 0.5. And then 1/2 squared is 1/4. 3 times 1/4 is 0.75, and 1 minus 0.75 is -0.25. Okay, so we'll draw our graph now. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, and then 1, 2, 3, 4. I'll notice that my y-asymptote, or my horizontal asymptote, is again y equals k, so in this case that's y equals -1. Make that a little neater. So I'll go ahead and graph. So -4, 11, -3 and 5, -2 and 2, -1 and a half, 0 and -0.25. So my graph is going to look like this. Arrows at both ends. Again, we have this nice exponential curve. This kind of curve is also called a hyperbola. Just as an aside, that's not terribly important, but if I use that name for this type or this shape of graph, you should just be like, okay, that's all he's talking about is the shape of that graph. The domain, as always, for exponential functions is all real numbers. The range is going to be, since the a value is positive, it's going to be k, which is -1, to positive infinity. And that's kind of all there is to graphing these exponential functions. That shouldn't be too bad. The other thing that I'd like to talk about today is exponential growth and decay models. So our general exponential growth model is y equals a times 1 plus r to the t. So a is like the initial amount or value or cost or whatever. R is the rate of change. And t is the time interval. And that interval needs to match the units for the rate of change. Decay is almost the exact same formula. It's just a minus r instead of plus r. And the a, r, and t all mean the same thing. Okay with that? So let's do a couple examples of kind of some story problems where we might need to apply these models. So I'm going to write one down here. Our first example is the story problem. It says in 1996 there were 2,573 known computer viruses. During the next 7 years, the number of viruses increased by 92% each year. The first part asks us to write a model for this situation. So the problem says that the viruses are increasing. So that tells me this should be exponential growth. So my exponential growth model is this. So the R is going to be 0.92. Again, I'm converting 92% into a decimal. And my initial amount of viruses, the thing that's changing, the initial amount is 2,573. The 7 does not go into my model. All that tells me is that this is good from 1996 through 2003. Right? That's all that 7 years is telling me, is that my model isn't good forever. It's really only good for that 7-year period. So plugging things in, 2,573 goes in for A. 1 plus 0.92 is 1.92. T. Then says to graph the model, and then to use the graph to estimate when, so the year, there were 125,000 viruses. So I'm going to use my graphing calculator to do this. Because I can get a much better estimate of when that's happening using the calculator's graph than a graph that I'm drawing by hand, because quite frankly, I can't be that neat. So I'm going to press the Y equals button and then clear out anything that I might have had in there and turn off any plots that might have been on. I'll do 2,573 times 1.92 to the x. Okay, and I'm going to set a window. So my window for the x's, well, this model is only good for 7 years, so I'm going to go from 0 to 7. And my x scale, I think if I'm going up, or if I'm only having 7 units on my x-axis, going up by 1 seems appropriate. The y-coordinate, again, the minimum value is that number of viruses initially. Just to have a round number, I'm going to do 2,500. And I don't know what the maximum value is, but I do know it has to be at least 125,000. So I'm going to pick like 200,000 just to be sure. And then, I don't know, let's go up by 10,000s or something. 200,000 is a big number, right? So the tick marks going up by 10,000 seems appropriate. Again, the scale doesn't really matter much. But I just wanted to pick my min to be something that's about the initial value, and my maximum needs to be bigger than whatever this value is that I'm looking for. So I'll hit graph now. So here's my exponential function coming in. So that's nice and pretty. To find the year when it was 125,000, I'm going to graph also y equals 125,000. And I'm going to find this intersection with my calculator. So just kind of eyeballing it, it looks like right around 6 years, or maybe a little bit less than 6 years. But let's find pretty precisely. So I'm going to press second and trace. This gives me the graph commands. I'm going to choose the intersect command and press enter. So now the calculator is going to ask me 3 questions. It says first curve. Notice my cursor is on one of the 2 graphs or 2 curves I want to find the intersection of, so I'll press enter. It automatically toggled to the next curve. That's what I'm looking to find the intersection of, is these 2, so I'll press enter there. And then it says guess. I could scroll over here, but it doesn't matter since there's only one intersection. I don't have to give it a good guess. It'll find it anyway, so I'll just press enter. So it says that intersection occurs at, let's say, about 5.95 years after 1996 would be my answer. And that's it. So let's do another example. So hold on a second, and I'll write up another story problem. So our next example says a new snowmobile costs $4,200, and that value decreases by 10% each year. So here we're asked to write a model for the situation. So when I read the story problem, I see that we're talking about the value is decreasing. So this tells me that we're looking at an exponential decay situation. So a times 1 minus r to the t. My a is going to be the 4,200. My r is going to be 0.10. That's again 10% written as a decimal. And again, we're given no time frame that this is good for. So we're assuming it's the life of the snowmobile. But that doesn't really matter to us because we're going to have a t in our model regardless. Again, a model should be a function. 1 minus 0.1 is 0.9. So it should always have two variables in it, a y and a t in this case. So then we're asked to graph the model and to estimate, or using that graph to estimate when the snowmobile would be worth $2,500. So again, I'm going to do this the same way that I did before. So I'm going to go in and I'm going to type in my function, which is 4,200. Oops. Times 0.9 to the x. And the value I'm looking for is 2,500. So I'll graph that in the other section. And now I'm going to have to reset my window here. So I don't know how long this is going to take, but I can't imagine that the snowmobile after 10 years is still going to be worth over half of its value. That seems like a long time for a for like a motorized vehicle, like cars and trucks and stuff, like lose half their value pretty quickly. So I imagine I'll have it for sure between 10. The minimum value that a snowmobile could ever be worth is 0, right? If it's decay, like it basically becomes like parts and it's worthless, right? It's just a rusty pile of junk. The maximum value that the snowmobile would ever be worth is whatever you paid for it, assuming that it's not a classic automobile or whatever. And since we're going from 0 to 4,000, I don't know, go up by 500 or something. Again, the scale doesn't really matter. It's just like the tick marks on the side. But I like to change them because I like to be able to get a little idea of what I'm looking at. And that helps give me a little bit of a reference point. Okay, so let's hit graph. Notice that here comes the exponential curve. And I already put in the 2,500. So that's in there well between 0 and 10. If I picked my x max and I couldn't see the intersection, I would just need to make that x max bigger until I was able to see the intersection. If you picked like 3 or something there for whatever reason, it'd be a silly thing to pick. But so let's find that intersection now. So second, trace, and I'm going to pick the intersect command. So 5. First curve, you notice that my cursor is on the exponential curve, which is one of the two curves I want to find the intersection of, so I'll press enter. It's automatically toggled into the horizontal line, which is the other curve I want to find the intersection of, so I'll press enter. And it asks for a guess. Since there's only one intersection, I don't really need a good guess. I'll just press enter wherever I'm at. And the intersection occurs here at 0.492. So the way I would answer this question is 4.92 years after purchase. Okay. There's one other situation that I want to talk about here as far as these exponential growth and decays go. And it's a special case of exponential growth called compound interest. So this has to do with like banking primarily. So if you put money in the bank, the bank pays you an interest for having that money in the bank, or if you make an investment, that investment, whether it's like a bond or a treasury note or something, will increase in value because you're essentially loaning money to the government and they're going to pay you an interest rate back on that. So our compound interest formula is this. So A is the value of the account. Let's just say value after T years. P is the initial value of the account, or the initial value. Also, this is called principal. Yeah, I was trying to remember if it was principal or principal. Spelling is not my strong suit. R is the interest rate, written as a decimal again. These rates always need to be written as a decimal. N is the number of compounds per year. And T is the length of the investment. So like how long has that money been in the bank? Okay, so the only thing that might seem kind of odd is this number of compounds per year. And we'll talk about, it's relatively easy to tease that out of the story problem to figure out what that value would be. So let's look at a quick example, and this will be the last example we look at today. So this last example says you deposit $10,000 into a bank account that pays 5.27% annual interest compounded quarterly. It says then what is the value of the account in 10 years, and then how long does it take for the value of the account to double. So here we're clearly talking about compound interest, right? Since we're talking about investing money into a bank account and having an interest rate. So this is definitely a compound interest problem. So we'll use our compound interest formula. So the initial value of the account is the 10,000. The annual interest rate tells me the value for R. So 5.27% as a decimal is 0.0527. Compounded quarterly tells me the N would be 4, right? 4 quarters are in a dollar. So it might say compounded yearly, might say compounded monthly, that's 12. Compounded daily, that would be 365. Compounded weekly, that would be 52. So it'd be something like that. And then it says for this specific problem, so in our case, in general, our model would look like this. And for this specific instance, where the t is 10, oops, I meant 4t up here. We would do that. So if I go to my calculator and just go to the home screen, so 10,000 times 1 plus 0.0527 divided by 4, oops, to the 4 times 10 is 16,880. And how many cents? 24 cents. Okay. Now in part B, it asks how long does it take for the account to double in value. So this is going to be a problem where I'm going to graph our general model and then graph, in this case of double, we'd be talking about 20,000 since the initial investment was 10,000, and find the intersection, just like we did in the previous problems. So my model is 10,000 times 1 plus 0.0527 divided by 4. And that's such a crazy decimal, I'm just going to type it in there so I don't have to do any rounding. And then 4 times x. And then we're looking for 20,000. And I'm going to set my window. Well, I know that it's going to be more than 10 years. 10 years got me to almost 17,000. So I'm just going to go with 20 years. That feels like if I could get, more than halfway there in 10 years, I should be able to get all the way to double in 20 years. And since we're going 0 to 20, let's go up by 2s. 20 is a lot of tick marks for the calculator to hold. The minimum value would be 10,000, right? That's the initial value of the account. It won't ever be less than that, worth less than that. And the maximum value, well, we need to see 20,000. So I'm just going to put 30,000 there. And maybe we'll go up by 5,000s, right? That's like 6 tick marks or something in between there. So that should be fine. Okay. So let's, got that all set. Okay, so let's graph and take a look. So here's my exponential curve for the value of the account. That's based on my model. And there's my 20,000. So here's the intersection that I'm looking for. So 2, 4, 6, 8, 10, 12, 14. So, somewhere between 12 and 13, but or 12 and 14, let's find that exactly. So I'll just do second and trace, intersect command, first curve, second curve, guess. So about 13.24 years after the initial investment. And my pen is acting weird now. But that's it. And that's it for this lesson. Okay, have a good day.